So welcome to the next chapter. It is turning effect of a force. We defined a force as a push or a pull on an object. We also know that a force can cause a stationary object to move or a moving object to come to a stop. Like friction. Friction is a force that opposes motion, and therefore because of friction, a moving object often comes to a stop. What we didn't know is that a force can also make an object to turn about a point. This turning effect of a force is what we call the moment of that force. So let's look at the moment of a force, or torque. And just like I've said, this is the ability of a force to make something rotate or turn about a point. And this word moment has nothing to do with momentum. Absolutely nothing. They are completely different ideas. We can also call it torque, but I'll stick to the word moment in this video. Now, when doing calculations, we either use m for momentum or the Greek letter tau, this funny looking t. I'm gonna be using the t. I prefer that because the m looks much like mass, so I don't like it that much. First, the terminologies, and the best you understand these, the better you get. And these include the fulcrum, point of application, and the line of action of a force. Fulcrum. The fulcrum is also called the pivot. If you have a seesaw, the edge point on which this bar rests is the fulcrum or pivot. It could also be this sort of a thing where you have a hinge, like the door hinges are pivots themselves. Then point of application and line of action of a force. Now there's this block resting on the ground. We apply a force on it, 20 newtons to the left. The point of application is this point where the force is applied. It's pretty obvious. What about the line of action? It's a line which passes through the point of application and goes in the same direction as the force. This is the line of action and extends indefinitely to the right. And this is a very useful concept, the line of action of a force. Because if you look at another force, 20 newtons to the left, in terms of magnitude, it's all the same. But it's got a different point of application and certainly a different line of action. The point of application is here, and the line of action will be that. Now, which of these two forces would you think will easily make the block to topple over, assuming the friction down here cannot allow it to slide? You know from experience that this 20 Newton force at the top is more likely to make this topple over. And the turning effect of this force depends on how far it is from the ground. Of course, the line of action doesn't have to be horizontal or vertical. You can have a line of force like that. What do you think its line of action is? You see, that would be the line of action, alright? Now we can go back and see what we mean by moment of a force or torque. But I suggest we work out some examples before I give you the definition. Look at this seesaw and just imagine what would happen if we put a 10 Newton weight on the right hand side. Okay? Now you don't have to be an elite physicist to know that the right hand side will go down. So the seesaw has rotated clockwise because of this force. We can say that the weight has a clockwise turning effect, or using a familiar language we can say that the force has a clockwise moment about the pivot. What I have to do to return the seesaw to level One thing I could do is to put the same weight to the left. The weight was 10 Newton. If I apply the same weight to the left, the same distance from the pivot, the weight will make the seesaw rotate anti-clockwise. So we can say that the force has an anti-clockwise or counterclockwise turning effect. Or in a more conventional way, it has an anti-clockwise moment about the pivot. So we get back to a balanced seesaw. Of course, I could have applied the same force at different points on the left, but obviously not the same force of 10 newtons. Of course, if you press near the pivot, you would need a bigger force to provide the same turning effect. Now let's look at this problem. There's a block resting on the ground. The bottom right corner is P. The bottom right corner there is P. Apply a 20 Newton force to the right and say the point of application is 2 meters from the ground. And I put the line of action. So the height of this line of action is also 2 meters. How do I work out the moment of this force about P? Now the moment of the force about P is, take the force 20 Newton and multiply by these 2 meters. That's the distance from the point P to the line of action. And this is the perpendicular distance. We don't take the distance from P to the point of application. No. We say from P, we take the perpendicular distance to the line of action, and that's the shortest distance from P to the line of action of the force so applied. And the moment is 20 Newton times 2 meters, which gives us 40 Newton meters clockwise. Look at the units. Newtons times meters gives us Newton meters, and state the direction as well. This time it was clockwise. Right, here's another example. Same object P, bottom right, but the force is applied at a different angle and different position. So how do we work out the moment about P? We draw the line of action and then the perpendicular distance from P to that line of action. There can only be one line that is perpendicular from P to that line. You know that from your geometry. The moment about P is, that's the line we want. I didn't measure it, I just assumed it is 2.5 meters. So the moment is simply 20 Newton times 2.5 meters, force times distance, which gives me 50 Newton meter anti-clockwise. So let's get the definition. We have the force and the point, which could be anywhere. So the moment of a force about a point is a product of, we multiply two things. That is the magnitude or size of the force, and this is important, the perpendicular distance d between the point and the line of action of the force. Important. So if you look at this diagram down here, we got the force F and we want the moment of this force about P. So draw the line of action, then draw a perpendicular from P to meet that line of action. That line there with length D. That's what we mean when we say perpendicular distance. It's that line from P to the line of action. and they are perpendicular to each other. It's that line from P to the line of action, and they are perpendicular. So moment is simply force times distance, that is tau is equal to F times D. Good. Time for an example. A 3-meter long horizontal plank is pivoted at its center. A vertical downward force of 15 Newton is applied at the left end. Now calculate the moment of the force about the pivot. You can try that. Pause your disc a bit and think about it. I hope you worked that out. Let's look at the solution. So here is the presentation of that information. Pivoted at the center means the force is 1.5 meters from the pivot or the fulcrum. Line of action of the force is here. Perpendicular distance from the pivot is the 1.5 meters. So moment tau is equal to 15 Newton times 1.5 meters, which gives us 75 Newton meter. 75 Newton meter. Another problem for you. This is a block. The bottom left corner is P. Put some dimensions here for you. And I put some forces here. And your task is to find the moment of each force about P. Pause the video and try it out yourself. Let's now go through it. Moment of A about P, we don't have to draw the line of action because it is obvious. It goes down through P here. That's 0 distance from P. So the moment of A about P is 8 times 0, which is equal to 0. And it makes sense because if a force passes through a, or rather if a line of action passes through a point, there is no moment about that point, really. B, the line of action will be vertically here. Its perpendicular distance from P will be 1.5 plus 2.5, which is equal to 4 meters. So the moment about P will be equal to 10 times 4, which is equal to 14 Newton meter anti-clockwise. Finally, C, the moment of C about P, it's simply 4 times 1.5. That is force times distance, which is equal to 6 Newton meter clockwise this time. And we wind up with this tricky one. The turning point is P. A force of 1 kilonewton applied in that direction. The line of action will be this. Then these dimensions and the angle of 60 degrees. And I want to find the moment of that force about P. Well, I hope you tried that out. Next, we'll look at parallel forces. Now, look at this illustration on your screen. Let's look at this diagram and see some few things. This diagram shows a meter rule which is horizontally suspended from two spring balances S1 and S2. We also have two weights W1 and W2 which are suspended from the meter rule. and their positions are adjusted until the meter rule is horizontal and the spring balances are vertical. Now what we need to do is to observe the readings on the spring balances S1 and S2. But again, note that the forces F1 and F2, that is on the spring balances S1 and S2 respectively, are acting vertically upwards, while W1 and W2 are acting vertically downwards. We also have a third force, W. Now it is the weight of the meter rule. You cannot ignore that. The meter rule also exerts some force downwards due to its weight. Then we measure the distances of the weights W1, W and W2 point, and I want us to select from point A, one end of the meter rule. So we'll have D1, D2, D3, D4 and D5. Please notice the distances are measured from point A to a particular point of interest. For now, what you will notice is that the sum of the vertically upward forces is equal to the sum of the vertically downward forces. So that if we take the forces in direction to be positive and those in the opposite direction to be negative, then the algebraic sum of the parallel forces is 0. To the moment parallel forces. Now in this illustration that we just looked at, the moments of F1 and F2 about the point A, which we selected as the reference point, are F1 times D2 and F2 times D4 respectively. Please make sure you notice that. Forces F1 and F2 produce anti-clockwise moments about point A, and their sum is F1 times D1, that is the moment for the force 1, plus F2 times D4, that is the moment of F2, force 2. The forces due to W1, W and W2 produce anti-clockwise moments about A. They pull that bar downwards. Their sum is W1 times D1, that is the moment of W1 about A, times D3, that is the moment of W about W2 D5, the moment of weight 2 about A, from W2 to E5. Be shown that the sum of clockwise is equal to the sum of anti-clockwise. The algebraic sum of the moments of parallel forces is 0. Another important thing to notice is the force due to the weight of the meter rule is shown as to be from the center. We call this the center of gravity. You're going to see when we look at the center of gravity that the center of gravity is a point object where all the weight is acting from. The next chapter. An example. When you are a uniform meter rule of weight 1.6 newtons supported by a spring balance at the 32 centimeter mark. The meter rule is balanced horizontally by a 1.2 newton weight suspended as shown on your screen. Now you need two things, that is the point where the 1.2 newton is suspended, and secondly the reading on the spring balance. Let's work that out. Now for A, since the meter rule is uniform, its weight is acting through its center of gravity. The letting the 1.2 Newton weight be d meters from the 32 centimeter mark to clockwise moments. We know that from. So the anti-clockwise moments 1.2 times d. Distance 32 centimeter mark to center, that is 50 centimeter mark. Centimeters. 50 minus 32 gives us 18. If you convert that into meters, it gives you 0.18. So we have 12d equal times. To finish your calculations, d is equal to 0.24 meters. Therefore, the 1.2 Newton should be suspended at the distance of, we again subtract 32 minus 24 centimeter mark, that is 8 centimeters. Part B, since the meter rule is balanced, forces the downward forces, and hence the reading on the spring balance is equal to 1.6 plus 1.2. Next, we look at equal parallel forces. Illustration on your screen. Now, on that figure, forces acting on a meter rule. The forces are equal, that's why I have designated both of them as F. But notice they are acting in. F is pulling upwards, the other is pulling down. You notice that they have equal magnitude. They are equal. Now, if the perpendicular distance between meters, then the turning effect will be calculated. Moments about a point P, any point P, and then say that P is L meters from one of the forces. So the moment due to that force is equal to force times distance, L. Alright? The moment due to the other force. So if the distance from P to one of the point was L and the total distance P, then it means the distance between P and the other force is minus L. Correct? So the moment due to that other force is equal to F force times the distance, that is D minus L. So F times L for the first force plus F times D minus L, which gives us FL plus FD minus FL, which gives us FD. The FL cancel out, they subtract each other. So the parallel forces is the product of one of the forces and the perpendicular distance between them. The forces is the product of one of the forces and the perpendicular distance. So let us take an example. The parallel forces mark and the other at the 80 centimeters mark. So if each of the forces has a mass of 3.6 newtons, calculate their moment on the meter rule about the 28 centimeter mark. Now the moment due to upward force, you can see that forces are acting is at the 28 from that P to the first force, that is at the 12 centimeter mark. The distance between that is 16 centimeters or 0.16 meters. To the other is 52 centimeters, that is 80 minus 28, which is equal to 0.52 centimeters. So in our solution, the moment due to the upward force, that is 3.6 times 0.16, force times distance, 0.576 Newton meter. Moment 3.6 times 52, again force times distance, which gives us 1.872 Newton meters. Total 0.576 plus 2.448 Newton. That's the Alternatively, we had said that the moment of unparalleled force is the product of one of the forces and the perpendicular distance between the two forces. So we could write the question alternatively and say total moment is equal to one of the forces times the perpendicular distance between them. The perpendicular distance between the two forces is 0.16 plus 0.52, which will give 0.68. So 468 2.48 Newton meter. The same answer with the first calculation. Now, to leave you with this question. Look at that plank resting on a full plates that are balancing on. The rule is suspended at the 50 centimeter balance. How far the weight be?
Into the mid-1800s, started with telephone, sending voice wires. By the 1800s, in those times, guys playing high voltage using a Rumkopf and passing this high voltage to tubes that had been moved the air, and they tried to see what would cathode ray. This is the size of the days. Now this is interesting because if you continue to experiment, what would happen? And this led not only to the discovery of the electron, but also some of us have had dealing in one way or the discovery of X-rays.